Hi, Alexis.
Hey,
how are you?
I'm not doing too well.
What's the matter?
Well, I'm confused on both quizzes, and I'm not sure I'm gonna turn them in because I don't know.
No, I want you to see what you're doing wrong. It won't hurt you because you've got plenty of quizzes. But I need to see what you're doing wrong, okay?
All right, because that the x tan inverse tan of the x, I don't know how to do that at all.
All right, let me tell you something, and I'll let you send it in. We have a series that's inverse tangent of x. If you look on page, wait just a second. Let me make sure everybody's in. If you look, there are certain series that we have. Let me get everybody in, and then I'll talk to everybody about it, okay?
Okay.
Okay. And then I'll bring it up and we'll look at it. What page was that? 8. Look at page 587 while we're waiting. Look at page 587. Hi, Deborah.
Hello.
There's Tiara. We just missing Dion. Tiara, did you get your quiz back?
Yeah.
Okay. Do you know what you did wrong?
Yes, I'm very disappointed in myself.
It was kind of, you did everything you needed to do, and then you're like, oh, you didn't do it. You forgot.
I literally forgot.
Yeah, I know. And I'm getting ready to talk to everybody else about that too. So I'm not going to hold it big against you. Okay.
I will. It's okay.
I know. You'll do that for me, right? Okay. So, okay, we got Dion in there. Okay, guys, 2 things. I don't know who has, if you hadn't turned in the Power Series representation, raise your hand. Okay. So Deborah, you've put it in, and Dion, you turned it in. Okay. So I'm getting ready to give Alexis kind of a hint. And if y'all got it right, great. If you didn't get it right, it's not going to be a big deal. Okay. And I want to tell everybody this. On page 587, there's a list of important series. And it talks to you about a number of things like how do you write a sine, how do you write a cosine, how do you write e to the x? There's a whole bunch of them there. So what we can do is create new series from these series. So for example, if you got in C, it's on 587. I probably should share this thing, but anyway, if you're looking at it, I'll say it. You've got a series for e to the x. If you want to find x e to the x, all you got to do is multiply that series through by x, and you'll have x e to the x. And Tara was having trouble with this with Lamar, and she said, I didn't think it would be that easy, and it was. It was the inverse tangent of x. We already had a series for that. If you look at its e on 587. So if you want to find a series representation for x inverse tangent x, you just take your x and you shoot it through that series. X times the first term will be x squared. The next one will be x to the 4th over 3, x to the 6th over 5. You just shoot the x through there, okay? So you can create new series really easily from these set of basic series. We've done all of them basically except f and g, which are functions called hyperbolic sines and hyperbolic cosines. I'm not worried about that. We're not going to worry about that. But A through F are like that. So let me share the screen, and I'll show you what the instructions look like. What's that, Alexis?
I have another question.
Okay.
Why did you give us that problem number 3 like that?
Like what?
Well, okay. The notation wasn't clear to me when I first saw it. Now that, you know, I had asked for help about it, it made sense, but I was just confused because, like, we haven't been notating the second derivative like that in a long, long time.
How did I notate it?
It took me like, I stared at that thing for
Oh,
30
I know.
I was so
Let
mad.
me turn my screen on. Yeah, but I mean,
And
okay.
the problem wasn't easy at all. I didn't even know, there was no example in my notes.
Yeah, there was an example in your notes, and I'll show you where it was. It wasn't with that function, but it was an example. Hang on, I'll show you. It's not a big deal. It's actually pretty easy. Okay, let me okay, let me get to something else. Okay.
The paper series that we did was so much easier than that. Like, that's why I was so confused.
All right, let me show you one we did, and it's not that it's that easy or that hard. One of them might look nastier than the other, but it's not really any harder or easier. Let me show you what I mean. Let's see if I can get my, okay, I'm gonna add a page here so I'll have something to write on. Okay, so there's a whole bunch of known series on that page. Down here. And one of them might be, for example, e to the x. All right, so e to the x was 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the 4th over 4 factorial plus so on and so forth, okay? If I ask you to find the integral from 0 to 1 of e to the x squared, this is sort of what I ask you to do, okay? But if I ask you to do that, you don't know how to do that. And I sort of mentioned this because I said that was a function we see in statistics a lot, but I don't, because I can't use substitution because I don't have a u and a du that'll work. Here's a series representation for it. If this is e to the x, doesn't matter what x is. If I replace x with x squared, I'm just going to write it like this. I'll write the series first and then I'll say what I'm going to do to it. It'll be 1 plus x squared. X squared squared is going to be x to the 4th over 2 factorial. X squared cubed will be x to the 6th over 3 factorial. If I raise to the 4th power x squared, I'll get x to the 8th over 4 factorial, and so on and so forth. That's the series for e to the x squared. Now what I asked you to do was integrate it and evaluate it from 0 to 1. Well, what we learned was that we can do this with a series by just doing every term. So first of all, if I integrate it, the integral of 1 is what? It's just x. The integral of x squared is x cubed over 3. The integral of x to the 4th is x to the 5th over 5, and I have that 2 factorial down there, so it's not going anywhere. This one will be x to the 7th over 7, and that 3 factorial is down there. And I don't know, however many terms you want to use. I don't know, I may have said 4 terms. But then you're going to evaluate it from 0 to 1. That's all you're going to do. And I'll plug in 1 for my upper limit and 0 for my lower limit. And you know what? If I plug in 0, everything's going to drop out. So I'll plug in 1 and I'll have an estimation of that thing right there. Now, the one I asked about inverse tangent, I know this isn't the one you're talking about, but I'll talk about it in a second. X inverse tangent of x, there's a representation for inverse tangent of x in your book. It looks like it's e, and it looks like x minus x cubed over 3 factorial. Is it 3? No, it's just 3. I don't have these things memorized. Plus x to the 5th over 5, and so on. And then it'll be minus x to the 7th over 7, and you kind of see these odd things playing out, okay? If you're asked to find x inverse tangent of x, then what you want to do is shoot the x through here. You can shoot it through the generic term if you want to. It'll just be an additional power of x. But now it'll look like x squared minus x to the 4th over 3 plus x to the 6th over 5 minus x to the 8th over 7. And that's what it'll look like. And suppose you wanted to find the derivative of that. Then you could find the derivative of all these things and you'd have an estimation. So I was going to say something else. Oh, if I looked at this as what it is, if you look at the generic setup of this thing, guys, it clearly alternates. And the generic setup of inverse tangent is the sum from n equal 1. Actually, n equals 0, I think, to infinity of -1. It's alternating to the nth, and it starts out with a positive, so -1 to the nth. I'll start at 0. And then at the end, you see x to the 2n plus 1 over 2n plus 1. And you can see that that works too, because 2n plus 1 is an odd number. And that's what you get. If you let n be 1, you'll get this minus. You put in 1 here, you'll get x cubed over 3, and so on and so forth. Now, if I want to find the series representation for that, what I want to do is multiply this by x. But I'm multiplying every term in it by x, so I'm just going to pull that x in there. Now let's look at what it would look like. N equals 0 to infinity. It's not going to change the alternation. Notice it didn't change it at all. X, now I'm multiplying it by here, so that means I'm multiplying this by another x. So I took it in. I took it in and did this. So what's x to the first times x to the 2n plus 1? What's the power on x going to be there, guys?
X to the 2n plus 2.
Yep. Everybody see why? I mean, you're taking like bases. You just add this power and that power, and it's still over 2n plus 1. Notice how these still stayed odd, but now these are even numbers. 2n plus 2 is an even number. It's one more every time. Okay. So that's the way they said this in the book. And again, I will get to your question, Alexis, but the way they said this in the book, it said, let's see if maybe it was in 11.7. Hang on. Yeah, in 11.7 on page 579, if you got your book with you, look at 15. Let me cut a light on, please. I can't see a thing. Everything's dark in here. Okay. It says, use a power series obtained in this section. In other words, use a power series we already know to write a power series for x e to the 3x. You know what? The one I know is e to the x. I'm going to start by putting a 3x everywhere there's an x, and then I'm going to shoot an x through it, and I'll have a new series. That's using one that I know. I'll say it like this. Use a known series. And the known series, guys, pretty much are the ones on that page we were just on, whatever the heck it was, 587, okay? And you can do that. Now, that last problem, here's the way I stated it. Now, as for notation, it says, we know that Alexis, read it to me. I can't quite remember what it was. Of 1 over x plus 1.
It was like d squared.
Yeah.
Over dx2 squared, and it was 1 over x plus 1.
Okay.
Equal 2 over x plus 1 cubed. Like, this whole problem just did not make sense to me at all.
Okay, listen carefully, because you're going to get it right on the test, okay? First of all, you have seen this notation. We didn't use it very much. It was the second derivative notation, Leibniz notation. And in Calc 1, we looked at dy dx. And then if you take the derivative with respect to x of dy dx, it's not a square, guys, it's another derivative. So that's why they put the 2 right there. It's the derivative of the derivative. So it's, anytime you see that, it's a second derivative. The third derivative, so the second derivative would look like this, of a function y, and then dx2, dy dx. The third derivative would look like d3y over dx3. Okay, so no, we have not used that one as much as we would use y prime and y double prime, okay? But here's the problem. Here's what you need to know about this one. So Are you okay with the notation? You're right. I mean, it's not.
Yeah, I just haven't seen it in a while, so I was just like,
know.
I didn't even know what to do with
I know.
it.
Okay, so let's see if I can figure. Let's see if we can figure out what it is. It says the second derivative of this is that. Okay, now here's the question. It says figure out what a series for this thing is. And you're like, well, that doesn't look like anything we've done. It doesn't look like anything we've had. It doesn't look like a geometric series. Does this one look like something? Does what's in here actually look like something that you might be able to work with?
Yeah.
Yeah, because it is geometric, isn't it? I mean, you could look at that as a over 1 minus r. You agree with that? So if I said to you, write this, and I'm going to change it already right here. Write this as a series. Tell me what you would do with it. And everybody watch. Tell me what you would do with it.
I'll say 1 divided by 1 minus negative x.
Good. Now what's r?
Negative x.
Negative x, and a is 1. So my series is going to look like the sum from n equals 0 to infinity of a times minus x to the nth power, right? Minus x to the nth power. So if I look at some, and actually, guys, I kind of don't like having the minus in there on that x, and I've seen some of you do this, and it's not wrong, but I kind of like my minus 1 to the nth outside, because that's sort of a hallmark of how this thing is alternating. Okay, so let's keep going. Let's write out a few terms. Let's write out a few terms here. Okay, so if I write out a few terms, if I let n be 0, I'm going to get that stuff to the 0, which will be 1. What's the next term going to be? Anybody? What's the next term going to be? If I let n be 1, what am I going to get?
0.
Well, if I let n be 1, I'll get minus 1 x to the 1, right? So everybody agree with that? If I let it be 0, I get things to the 0, so that's 1. What's the next one going to be? Let n be 2. What are you going to get here if you let n be 2?
1.
Mm-hmm. N is 2. X to the second.
Oh, I'm still looking at, okay.
Oh, are we okay? Are we okay?
No, I just didn't know which, I don't know. At this
That's
point,
all right. Here, look at that. That's the one I'm putting into. I haven't gotten to the punchline yet, so just give me a minute, okay? All we're doing is screwing around with this thing right here. We know how to do that. So what's the next one what's the next term gonna be in this one?
Minus x cubed.
Thank you. Next one. I'm almost done.
Plus x to the 4th.
Plus x to the 4th, minus x to the 5th, and so on. That's the series for 1 over 1 plus x. Everybody with me? Okay. Now, here's what the problem said. Let's go back to what the problem said. It said, the second derivative of this one I know is the one I want. Well, I just wrote the one I know as a series. So how am I going to find, if I take 2 derivatives of it, I should have 2 over 1 plus x cubed. So the whole point here is that you can take derivatives and antiderivatives of this. So if I took the first derivative, I'm going to erase, that's too close for me, but let me show you something. So the first derivative would be minus, you help me here. If I bring that up to the minus 1, it's be minus 1 over 1. What's that? It's minus 1 over 1 plus x to the second. Okay? If I took the first derivative there, well, there's the function, that first thing, right there. The first derivative is going to be, you're going to take the derivative of that. That's the representation of the function. So the derivative of 1 is 0. This will be minus 1 plus 2x minus 3x squared plus 4x cubed minus 5x to the 5th, blah, blah, blah. Now I've got a representation for that function, the first derivative of the one that I knew. Okay? The next derivative, if I bring that up to the minus 2, it'll be 2 over x plus 1 to the third, or to the minus third. So I'm going to put it down in the bottom. Well, if I want that one, it's the derivative of that, I'm just going to take the derivative of the one before it. So the derivative of minus 1 is 0. That'll be 2 minus 6x plus 12x squared minus 20x to the third, blah, blah, blah. Now I got a series for that. The bottom line here, guys, is you tag on to something you know and say, well, if what I want is the derivative of that, I'll just keep taking derivatives. If it's the antiderivative of that, I'll take integrals. How's it look now, Alexis? Your question.
Like, I got to that point, but I still don't know, like, what, like, I just didn't know how to write it. That makes sense, because, like, it's still not making sense to me at all. Because I was taking, then I don't even know what I did, honestly, because when I kept looking at it, it just doesn't make sense to me.
Right.
I don't know how to explain it.
Here's what we say about series. We say you can differentiate them term-wise. That means if you got a series for a function, you want to find the derivative of whatever that function is, you can take the derivative of the series and you'll have an estimate there. So if I wanted to know what the value of this function was at 0.1, I could plug in 0.1 here and find it on the calculator, or I could plug in 0.1 to a bunch of these terms and also find the same thing. Well, something close. The more terms you have, the better it is. That's what a series is. And this is not easy stuff that all of a sudden you think you've got it and then all of a sudden it's gone. Okay, it's like it. So you got to sort of keep thinking about what you're doing. You're just writing these representations, these polynomial representations of these functions. And all we've really got to hang on to is some geometric stuff, which is where we got started in that, and some other functions like e to the x, some known functions. So do you have another question, Alexis? Sorry.
Yeah, so like I guess maybe I'm getting confused on like the representation. So you want to represent it like that, like a series, or like just individual terms? Because that's what I'm confused about.
A series. The whole thing is the series.
Okay, so that's the series that you wanted us to represent?
Yes, that's the whole, I mean, and you could write more terms and you might be able to find a pattern here. I don't know. It's harder and harder.
I thought you wanted to draw that squiggly thing. That's why
okay, I can do that. But let me show you something.
I couldn't do it. So that's why.
Well, I'll tell you how to do, that's a good question. That's a really good question. Let's talk about it, because Tiara tried to do it and she forgot something that you have to do when you differentiate. Do you remember what it was you forgot, Tiara?
Yeah, I had into the 0 and it was supposed to be into the 2 or something.
Yeah. Look at this, guys. Look at what this one looks like. Let's look at the 1 over 1 plus x. If I write that thing with the squiggly thing, otherwise known as a summation sign, okay, I can write it as the sum from n equals 0 to infinity of, well, let's see, it alternates. So I'm going to have minus 1 to the nth. It's got all powers there of x to the n. That's what it looks like. Okay. You know what? This is easier than you think it is. If I want to look at its derivative, which we said was minus 1 over 1 plus x squared, this is its first derivative, I can write the terms out, or I can differentiate this thing, guys. It's no different. Look at this. And I'm going to leave that as a question mark right now. Minus 1 to the n is just going to be minus 1 to the n. Okay, that's what makes it alternate. What's the derivative of x to the nth power of something?
N to the x, n minus 1.
Okay. Ladies, you see what Tiara said there? You just bring the power down and take away 1, right? So I just differentiated it. If you want a representation for a derivative and you're coming from this form, or you know what that looks like, just take the derivative with respect to x for that unknown n. Now, I will say something here that this is important. When you let n be 0 in this first one, you had something like this thing to the 0 power, which was 1. If I started at n equals 0 on this one, because you brought down that n, what would your first term be if you started at n equals 0? Well, if n is 0, what's going to happen to the first term?
It's going to drop out.
It's going to drop out. So when you differentiate, your power typically goes up 1. Because what's going to happen is when you differentiate, that that it would have been x to the 0 there. You had this n, now it's going to be, if you let n be 0, it'll be 0. Let me show you what I mean another time. So see if we get what we wanted. Here was the series. And I don't know, I can't remember what I asked you on that quiz in terms of how I left you to, I would have taken this, all right? But it's nice to see this too, and that's what you'll see. But if I say, let's figure it out. If we let n be 1, it'll be minus 1 times x to the 0. Well, minus 1 times x to the 0 is minus 1. Yep, that's the first thing I get. If I let n be 2, it'll be positive number. 2 times x to the 2 minus 1, it's 2x. Yep, that's what I get. All right, I'm going to look at the next one. Now, the next one is 2 over x plus 1 cubed. You know what? I wrote the terms out, but you know what? I can do it down here. I can do it with that. Minus 1 to the n, that doesn't have an x in it. I'm not going to differentiate that. It just makes it alternate. Now, there is an n here. How do you take the derivative of x to the n minus 1?
Bring down the n minus 1.
Remember how it's just a power rule, isn't it? You bring down the n minus 1. And Alexis, you tell me what the power on the x is going to end up being.
N minus 2.
Yes. Now, I wrote a 1 there just because I did it out of habit. But you know what? If I let n be 0, this whole thing, the first term just wipes out. So, I mean, if n is 0, it wipes everything out. If n is 1, it wipes everything out. So where should I start? What's the first thing that's not going to wipe things out? 2. And see if we get the right term. If n is 2, I'll get a positive 2. 2 minus 1, that's 2 times 1. X to the 2 minus 2 is x to the 0. That's exactly what I got. I got a 2 there. So you can differentiate these things just the same way you differentiate any n. Does that seem better to everybody?
Not really, but you know, at this point, I'm still having trouble just understanding like the whole concept, but I don't know.
Well, let me. I wrote a review sheet for you guys. Okay, I had already written sort of a summation of the things we've done, but I sat down and wrote out something by hand yesterday, and I put some practice problems on it. Okay, and I put it on Moodle. So I want you to, first of all, I do want these quizzes. I need to make sure you kind of, and I would like for you to do this. If you didn't send it to me, just do it and send it to me, okay? Because I want you to have the thought about what was she doing, what am I doing here? And then the Taylor series and the Maclaurin series isn't too bad. What the Taylor series and the Maclaurin series do is give you a way to find series for things you just don't have anything to hang on to. It tells you what the coefficients have to be with that little formula, f prime of c over n factorial, okay? So that you got to see the big picture there about how we're writing these series. So look at those again, and I want to see I want to see the Taylor series one because I need it by tomorrow. Because I really want to. I want to make sure. I want to see what you're doing wrong, and I want to see what you're confused on. And I want you to tell me what you're confused on, which is what you're doing right now. Okay. Question? Anybody? Look on the get it off Moodle. Get the review sheet off Moodle. Okay. And here's how I'm gonna tell you how to study for your test. Study your quizzes. So get a quiz to me. I don't care if it's late at this point. It can't be, but so late. But get it to me so I can mark it and say, here's what you don't understand. Okay. Okay. So what I want to do today is I want to talk about some of the polar coordinate stuff. So we're going to play again today. This was not going to be on the test, but I want you to know how to find your way around these polar coordinates. So let me get back to that, wherever I was. Guess I was right here. Yeah. Okay. I gave you some homework yesterday that talked about changing polar to rectangular and rectangular to polar. And from what I'm hearing, I don't think you looked at it. But we're gonna do some. You may have.
Can we look at B?
Huh?
Can we look at 3B?
We're gonna look at every one of them, okay? Here was
Okay.
the homework, and here was what I asked you to do. And here were the relationships between rectangular coordinates, X and Y, and these polar coordinates. Now remember about what polar coordinates meant. They meant you located a point by knowing what angle you went and how far you were away from the axis, the origin. That's all a polar coordinate does. So let's make sure we understand what it's doing. So if we set up a triangle here are the relationships. X is going to be r cosine theta, because there's X, there's Y. That's what that looks like. R is just the hypotenuse of that thing, so it's square root of x squared plus y squared. R squared is square both sides, you get x squared plus y squared. I had asked you to plot, some points. And so I want us to look at how we plot points and make sure everybody's good with that. So if I ask you to plot 4 pi over 2, I'm gonna come to this thing right here, I'll put it in. 4 means you're gonna go 1, 2, 3, 4 circles out, and pi over 2 is right there. That right there is 4 pi over 2. Okay, so 4 circles out, 1, 2, 3, 4, I got it, go up pi over 2. That's what that means. What would be the rectangular coordinates for that point, guys? Just look at it and tell me what the rectangular point would be. What would the x coordinate be?
0.
0, and the y coordinate would be what? 4. Yeah. So, all right, let's look at another one. I ask you to plot 0, 7 pi over 6. Now that says r is 0. Well, r being 0 means I don't go anywhere away from the origin. I don't go out anywhere. R is 0. The distance from the origin is 0. And honestly, guys, it doesn't matter that it's 7 pi over 6 because you don't go anywhere. So 0, 7 pi over 6 is right there. I made the statement yesterday that you could have any point with a 0 on it, and it didn't matter what the angle was. It still was that point. It was the origin. That's how you make the origin. Look at this one right here. I'm gonna hold on that third one. 3, 4 pi over 3. I'm gonna get on the circle 1, 2, 3 and go to 4 pi over 3. And if you know your unit circle, you'll know that 4 pi over 3 is down here in the third quadrant. So 1, 2, 3, I'm on the circle 3. 4 pi over 3 is right. I can't see, I've got a bad glare here, guys. There's 4 pi over 3 right there. So I got on the circle 1, 2, 3, and the angle right here was 4 pi over 3. God, that looks weird. Can y'all see that? My skin came out really badly. So that's what that looks like. Finally, this last one, this was a funky thing that happened with these guys. We don't have a whole lot of time to talk about why, but this one says -1, 5 pi over 4. So let me tell you how we're gonna do the ones with r equal minus. First of all, we know we're gonna be on the circle 1, but what we're gonna do is go to 5 pi over 4 first. So if I go to 5 pi over 4, 5 pi over 4 is that ray right there. That right, let me erase some stuff off this. That ray, 5 pi over 4 is right here. Wow, I wish I could have left it like that. See it? That's 5 pi over 4. Now, tell me what's directly across from that. I've got a little wiggle in my line, but what's directly across from that? Pi over 4. What happens on these is that it jumps you over to the opposite quadrant, to the diagonal quadrant. Again, that's a weird thing that happens here. But you go to the angle and then you jump over to the opposing quadrant and stay on the one circle. So in other words, that point is equivalent to the point 1 pi over 4. You end up in the same place as if you put -1, 5 pi over 4. That always happens like this. The angle, if that happens with this r being plus or minus, sorry, if this r being plus or minus, these two angles always differ by pi. Because if you go straight across from something, the angle in there is pi. All right, let's look at the next. I assigned some more, I think. Some of them, the second part, I said change to rectangular coordinates. If these are my polar coordinates, that means r is 5 and theta is 3 pi over 4. We know x is r cosine theta. So all I have to do is put in my r, put in my theta, and I got minus 5 root 2 over 2. And for my y, it's r sine theta. So I got 5 times the sine of 3 pi over 4, and it's 5 root 2 over 2. If you think about this, it would be in the second quadrant, because if you plotted it in polar form, it would be on the circle 5. 1, 2, 3, 4, 5, and 3 pi over 4 is right there. I lost it. 1, 2, 3, 4, 5, right there. That's where that would be. Notice it's in the second quadrant. Notice when you changed it to rectangular coordinates, it was a point with a negative x coordinate and a positive y coordinate. That's in the second quadrant. This one right here, guys, this is one of the funky ones. I keep putting them in there. If I change that
for a while.
Say it again. Uh-oh, my internet's going wonky. What? Say it again.
You were frozen for a while.
I was. How long? Did everybody hear me say anything? Did anybody hear me say anything about A? R is 5. We know R is cosine theta, so I put in 5 and I put in 3 pi over 4. And for Y, it's 5 sine theta. All I said was it's in the second quadrant, and so would it be here if you put it at, that would be another representation of that point. That's 5, 3 pi over 4. If you found the X and Y coordinates, it'll be that root 2 over 2 thing. The next one, if there's a minus here, guys, I said in order to change it to a plus, you need to go pi units straight across. If you go straight across from 11 pi over 6, it'll be 5 pi over 6. So now you can change this. X is R is 2. Cosine 5 pi over 6 is minus root 3 over 2. So that point is minus root 3. And Y equal R sine theta. That means 2 times a half is 1. So there's the point that would be corresponding to that point in polar coordinates. The rest of them are not hard. If R is 3 and the angle is pi over 6, X is 3 cosine pi over 6. Cosine of pi over 6 is root 3 over 2. Y will be 3 sine pi over 6. Sine of pi over 6 is a half. 3 times a half is 3 halves. And I get that. So that's the same point in rectangular coordinates as that is in polar coordinates. What quadrant will this thing be in, guys? What quadrant will that one right there be in? If you're on the circle 3 and you only go pi over 6, what quadrant are you in?
First.
Yeah, you're in the first. And notice my point in rectangular coordinates came out with 2 positives. X positive, Y positive, first quadrant. Finally, on that, and then we'll do 3. I got more to do on 3 too. If I let R be 2, and I let theta be 3 pi over 2, X will be 2 cosine 3 pi over 2. Well, the cosine of 2 pi over 2 is 0, so the X coordinate there is 0. Y is R sine 3 pi over 2. Well, the sine of 3 pi over 2 is minus 1. This point is the point 0 minus 2. And you can see that, guys. If I look at this, 2, 3 pi over 2. 2, 3 pi over 2 means I'm going to get on the circle 2, 1, 2, and go down to 3 pi over 2. Put my pen on. And you can see that that's in rectangular coordinates, that's 0 minus 2. 0 minus 2. I'm sorry this didn't print out. I wasted so much ink trying to print this thing out to tape on this thing. Okay, all right, let's look at 3. This is the one, Tara, is this the one you were asking about?
Yeah.
Okay, here's what I'm gonna do. I'm gonna change it to polar coordinates. Here's X and Y, right there. R is the square root of X squared plus Y squared, so that R is gonna be square root of 13. So you'll be on the circle square root of 13. That's somewhere between the square root of 9 and the square root of 16. So it's somewhere between 3 and 4, okay? If I want to know what the angle is, if you think about these things, remember the sine was r cosine, I'm sorry, the sine was r sine theta, and the cosine was r, the y was r sine theta. If you put those two over each other, you get the tangent is the y coordinate over the x coordinate. A y coordinate over the x coordinate. And then do the inverse tangent, put it in radians. That's what it's going to be, minus 0.5880. Guys, anytime you want to find the angle, that's the one you want to go to. You want to go to the fact that, let me move up here a little bit, that the tangent of the angle you're looking for is y over x. If you're wondering why, again, if you look at this, if you looked at this thing right here divided by this sine divided by that, the r's would cancel. Sine over cosine is tangent, and that's y over x. So you put those two things together, you get tangent of the angle is y over x. So put r sine theta over r cosine theta. The r's go, you get tangent theta is y over x. That's what it's looking like. Did you just know where to start on that, or how to find it on the calculator or something, Tiara? What happened?
I got that one, but I can't get B.
Okay, let's look at B. B is one I didn't even use a calculator for. I used the unit circle. Okay, so the tangent is this, here it was. The tangent was y over x. So the question is, do you know somewhere, damn it, sorry, excuse me, pardon my French. I don't want that, get out of here. Do you know anywhere on the unit circle, I don't even know where I was, here we go. Do we know, this was y, this was x. Do you know anywhere on the unit circle where you've got a point that looks like minus a half root 3 over 2? Minus a half root 3 over 2. You look around, I think you'll see it's 120 degrees. Got it? All right, I like that smile. So guys, if it has root 3s and over 2s and halves in it, go to the unit circle, don't go to the calculator. You should be able to do it without it. Okay. Couple more things. Okay, there we go. What I wanted to do is talk to you about equation conversions. Suppose I have this thing right here. I know that's a circle with radius 2. I know that x squared plus y squared is r squared. So if I put that, remember how r was the square root of x squared plus y squared? That means r squared. That means r squared is x squared plus y squared is 4. That means r equal 2 is the polar equation for a circle with radius 2. In polar coordinates, circles that are centered at the origin are the easiest things to do. R equal 5 is the circle with a center at 0, 0 and a radius of 5. In other words, it's on there, you just draw the ring at 5. If R is 3, it's the ring at 3. The other thing that's easy in polar coordinates is the angle. Let me look down here. If I say graph theta equal pi over 4, we know what? All you're really doing is graphing. If I go back up to here, here's pi over 4 right here. There's pi over 4 right there. Theta equal pi over 4 is that ray. So the easiest things to graph in polar coordinates are circles centered at the origin. So what circle is that, guys? 1, 2, 3, 4. That equation is r equal 4. R equal 4. This equation is theta equal pi over 4. How would I name the x-axis, guys? What's that? Theta equal what? Oh, I already wrote it up there, didn't I? Theta's what?
Pi over 2.
Okay, those are the easiest things to graph in polar system. What are the easiest things to graph in a rectangular system? Vertical and horizontal lines, because they line up with the kind of things you're looking at. They line up with a grid. They line up with a grid that's got vertical and horizontal lines in it. My easy things in a polar system line up with circles and rays. It's just a different way of looking at things. So I'll go down here and look at this example. Suppose I said to you, I want to know what x equal 1 is in polar coordinates. It's easy in rectangular coordinates. Well, I know x is r cosine theta. If I divide by cosine theta, I get secant theta. That's not real pretty there, guys. A vertical line in polar form is r equal a secant. R equal a secant. You can kind of guess what y would be. And if it were 2, it would be 2 secant, okay? If y equal 1, we know that y is r sine theta, and that's 1. Divide by sine, we get cosecant. A horizontal line is a cosecant. That's things that are easy in one are messy looking in the other one, okay? All right, let's do one other one here. And then I want to, I got something I want to show you, and then we'll call it a day, and we'll come back and play tomorrow immediately with the calculator, because that's what I wanted to play with today, and I didn't quite get to. Look at this. R equal 2 cosine theta. Suppose I said I want to change that to rectangular coordinates. All right, I'm gonna go down here, guys, where I got a better piece of paper. Okay. I said I wanted to change R equal 2, did I say sine theta or cosine theta? It doesn't really matter. I don't care.
Just sine.
Did I say sine? I'll do sine. I'm going to show you what this is in in rectangular coordinates. Well, first of all, I know R is the square root of x squared plus y squared. I also know I don't like screwing around with square roots, so I'm going to square it out. I know that's what that is. So I'm going to zip an R through this in order to take advantage of the fact that I got rid of that square root. And it also fixes something else up for me. R squared is x squared plus y squared. That's equal to 2. Guys, what is r sine theta? What is r sine theta? Which one was that, x or y?
Y.
It was y. It was y. All right, now, here's the question. Do you know what that is in rectangular coordinates? Well, it's got an x squared and a y squared in it, and the coefficient is the same on the x squared and the y squared, but it's, I don't know, it's got an x squared and a y squared in it. What is it? What do you think that is, guys?
Implicit.
Well, I could differentiate it if I want to implicitly differentiate, but I don't want to do that. I just want to know what it looks like. Here's, and maybe I'm gonna move the y squared over and see if you recognize anything I'm doing. I am going to complete the square on this. And I'm going to take half of minus 2 and square it and add it to both sides. This says I've got x squared plus y minus 1 squared equal 1. That, my friends, is simply a circle that's been shifted over. If you think about what you're doing here, the center of this thing, the center of just one centered at 0, 0 would have a 0 and 0 in both places. This is centered at 0, 1 with a radius of 1. That's a circle centered at 0, 1 with a radius of 1. If I were to graph it, and this is 1, it's centered at, and this is minus 1, and this is 1, and this is minus 1. 0, 1 would be right there. That's the center. This thing will look like that. If you put it in your calculator as r equals 2 sine theta, and it's in polar coordinates, that's what it'll graph. That's what it'll graph. Okay. All right, I'm going to cut the homework down drastically tonight because I didn't quite finish what I wanted, but I'm going to, oh boy, I'm going to give you some of those equations to like decide what they are in different coordinate systems, page 667. And again, guys, write this down because I'm kind of wildly changing things here at this point. Page 667. And the ones I want you to do, they're not too many of them. Just use these conversion formulas to do 1 through 11 odd. No, I don't want you to do those because I hadn't talked about sketching yet. I want you to do 27, 29, 31, 37, 39, and 49. These are going from rectangular to polar. These are going from polar to rectangular. That's all. That's it. Send me quizzes, please, so I can see what you're doing right or wrong. Has anybody turned in the Taylor quiz, Taylor series or Maclaurin series yet?
I'm turning it in after this class.
Okay, all right. Everybody turn it in so I can see if you're computing the coefficients properly, okay? Because that will definitely be a problem on the test, and it won't look very different from what you've got, okay? We'll come back and we're gonna play on the calculator tomorrow. I'm gonna go back and play on the calculator simulator that I've got, so you need your calculator to play with, okay? Questions? Anybody? Smile, it's almost near the end. This has been a long, hard ride here, guys, but we're making it, okay? So I can't see Tara's eyes because she got her hands over her face. Okay, all right. I'll see you tomorrow. Bye.